Okay, so our exam is Thursday. Okay, so in the exam 3 related quizzes folder, again, you got your review outline, and then you've got okay, so there's a review outline, the quiz 6 with solutions, quiz 7 with solutions, quiz 8 with solutions. And then I will put up, you're turning in quiz 9, right? So let's do that now. Make sure your name is on, no fold. If you didn't staple, make sure your name is on all pages. If you didn't staple. We're not going to turn in that homework. Not to diminish its importance.
For some reason,
Any more quizzes? Okay, so I'll put up a blank version and a solution to this. I put up, if you go to assignments, I put up, let's see, in Wednesday when we turned in that optimization homework, I put up solutions to those problems. Some of those are actually written out solutions. Others are a link to a video where I do the problem. Okay. That cup problem, the one where you cut out the wedge and then you fold it up and make that cup, the volume of the cone, and you're trying to maximize the volume of the cup. I put on a second video which shows a way to make that, taking the derivative and doing the algebra, a whole lot easier. Okay, it's kind of a trick or a strategy. So there's actually 2 videos for that one. But so notice for your studying optimization, the solutions to all those problems that we worked on for a week or so.
So it was under assignments?
Yep, it's where that was due. So the day that we turned those all in last Wednesday 27th. I've put on my math lab, I put review sets for everything we've done for this exam. They're the ones that start with R. So those are all there. So you can work and redo those problems over and over and over again. There's no limit. And see the answers and practice there. What else? Oh, so tomorrow, so this week in recitation we will have a quiz. The first half of the quiz will be optimization problem, which is on your exam. The second half will be the current stuff, which is on the final. Okay, so the first half of the quiz will be an optimization problem. The second half will be current material. So normal quiz week this week for recitation. And then our exam is Thursday. If you haven't started studying yet, don't wait. Start tonight and parse out your studying in many sittings. Same procedure as always. Testing center, you go between 10:30 and 6:30, and you have until 8. They collect all the exams at 8. So same procedure. All right, so lots to talk about there in terms of preparing for the exam and the exam. Anybody have a question? And then...
Will there be a review guide for the final?
Yes. Yes, there will. Other questions about this week exam? And then our final is a week from tomorrow night. A week from tomorrow night, which is, I can put that study guide up soon, and then It covers everything with an emphasis. There's a little bit more of an emphasis on the stuff since the third exam, because this is the pinnacle. Today's a great day. It's just kind of do the fundamental theorem of calculus, which we'll find out we've been doing all along. Okay? All right. Any questions? Yes, ma'am.
For the final exam, when we have stuff like the volume of is the formula for the volume given, or should we know?
Basic, so you should know area of a square. You should know the area of a circle. But more complicated ones I would give you. Yeah, but so basic stuff, I'm going to assume that you know. Other question, volume of a cube, you'd have to know the volume of things like that. Or volume of a rectangular solid. These are all things you should know. Okay, so last time, Melody asked a very good question that kind of brought up an issue that we really didn't, we kind of had a hole in our thinking, and so I got to thinking more about it, and I thought this is a good opportunity to patch up that hole and bring more coherence to what we've been talking about, okay? Some more coherence, because that was a very, and you'll see, we'll talk about the question in a second, but let's just review here. So if we have a rate of change function R, can you write the accumulation function defined by R? We should all be able to do that. What's the accumulation function defined by R? Think of it as a quiz. Everyone should be able to do it. Write an accumulation function defined by that rate of change R. Janae, what do you think? Can you do it? You got it. Integral from a to x rt dt. Okay, and I've called that function capital F of x. But now we know something more than we did at the beginning of the semester, where f of x is capital F of x is what? What is capital F of x? How could you define, or how could you talk about what capital F of x is? Nicholas.
One of many accumulation functions for the rate function.
Okay, and now in terms of how does that relate? She's saying it's one of many accumulation functions associated with that rate function. Good. And how are those two related? How are F and R related? Yeah.
R is like two small parts of x when added together. When you add all the parts of R together, you remove the x, which is the endpoint.
I'm just in general, what is that R function? How are the R function and the capital F function related? And so they're, yeah.
R is the derivative of F.
So R is the derivative of F, which makes capital F. And that's what you were working on in your homework, right? You're working on finding antiderivatives. So this is review. Okay, so we have a rate function. We can build the open form accumulation function, and now we know the closed form then is built from an antiderivative of the rate function. We good? Okay, so now so let's take a look at the sand example. Dumping sand onto a scale. I've got the rate of change of dumping the sand. So first a little bit of sand falls, and then it all kind of goes in a heap at the highest rate, and then there's just a little extra, and so the rate slows down, right? So that's kind of realistic of how we might imagine rate falling on the scale. And then we have the accumulation of the weight over here on the right. This will look very familiar. Okay, so suppose at c seconds we reset the scale, and this is the common thing. Like on a scale, you can like recalibrate it. So you push a button, and it just resets it to 0 weight, even if there's stuff on it, right? So you familiar with this? Yeah. So you can have some stuff on it, and you can hit this button, and now it makes the weight 0, and now the additional amount that you add gets weighed, right? So we're going to do that. So say along here, say it's c seconds. Anytime c, that's here and that's about here. We're going to do a reset, okay? We're going to do a reset, but we're still thinking about accumulating to any value x. Put it in the wrong place. Try again. C, and then x. So we're still accumulating, and a is in this case is 0. Still accumulating, starting at a up to x, but along the way we do a reset. We do a reset on the scale. Okay, so then we can think of that the accumulation of weight from a to x as having the total weight of sand, right? The total weight of sand at x seconds on the scale as having 2 parts. We can think of that accumulating up in 2 parts, right? So it would be the weight accumulated in the first c seconds, which would be the integral from a to c, plus then the weight accumulated after the reset from c to x. This should be pretty easy. Does this make sense? Anybody have a question on that? So the total amount that's accumulated in the scale, we can say is the accumulation from a to c, and then we have this reset, and then we accumulate from c to x, and we just add those up. And we have this same as the total weight on the scale. Okay, so how can we then write? Question? Then how can we write this integral? So over here, what is the accumulation from a to x? How can we rewrite the accumulation from a to x? Please, somebody know this. Yeah, so how can we, now, so like here, this is open form, right? So can we write it a different way? Aaron?
Accumulation from a to c plus the accumulation from c to x.
Okay, right, that's this. Okay, that's true. But just this expression right here. Christian?
F of x minus f of a.
Okay, but, which is just, yeah, it's just f of x, right? It's just f of x. And what about from a to c? It's right here. So it's basically, so f of x right here, f of x gives us the total accumulated weight in those first x seconds, right? And what about in the first c seconds? Yeah.
F of c minus f of a.
No, in the first c seconds.
Oh.
Yeah, so that's true, but that's just f of c, right?
Oh yeah.
We could do the f of a, but we're there's at a there was 0 on the scale. Okay, there's nothing on the scale at 0. Okay, so therefore, what is the accumulation from c to x? Yeah,
Oh, that
James.
came out loud, sorry.
No,
F of x
please.
minus f of c.
Yeah, f of x minus f of c, right? So this isn't, I'm just giving you a context to think about, and there's really nothing new here, okay? Except this idea of a reset, If we reset the scale, then the scale reading, this is kind of like the scale reading now, right? This is like the scale reading. And when it would start at z, or at c, we get a scale reading of 0, even though there is already this weight on the scale, okay? So now this goes to the question that was asked last time. Okay, does this make sense? Okay. So suppose we have this rate function. And this is one of the ones in your homework. -5 cosine x to the 4th sine x to sine x. This is one of the rate functions you did in the homework. Okay, so This rate function, just as it is, we can think about that the rate and the associated accumulation begins, or like what we call A, begins way out to the left at a very large negative value. So if I were to show you, this just goes way out to the left. And we can think about the accumulation, the rate and the accumulation starting way out to the left. And then working its way for x positive. Just gonna reset the graph here. Okay? So then, if that's the case, if the rate and the associated accumulation brings way out to the left, then what would this represent? What would this represent if the rate of accumulation starts way out at negative, almost negative infinity, and then we let x increase? Then how can we make meaning out of this?
Is that 0.5?
0.5, yeah.
Is that just the point where we start measuring accumulation?
The point where we start measuring accumulation. Has there been accumulation before that?
Yes.
Yeah, there has been before. So how can we think of what this 0.5 is? It's like a reset. You see, it's like a restart. It's like we're gonna reset so that what's gonna happen at 0.5? Well, we've started accumulating way out there. It's gonna be 0. You see, it's gonna be 0. So rather than thinking of this as we're beginning accumulating at 0.5, we can think of the accumulation Rx that has a reset or a restart at 0.5. So that because we know it's going to be 0 there, right? We know it's going to be 0 there. And then this kind of, the question was, what about, why is there a rate and accumulation over there if we're starting at 0.5? Okay, so we think of, it has already started, and by creating this accumulation function, it's going to be 0 at 0.5, or like a restart of the accumulation. Does that make sense? So let's graph that. And there we see at 0.5, sure enough, we have our 0. Okay, so look, can we write that, so for practice, look, can we write that in a closed form? So this is I've graphed the open form of that accumulation function with a restart at 0.5. Can we write it in closed form, which means being able to do what? Writing it in closed form means being able to see what function that is the derivative of, right? And that's what you practice in your homework. So what function is that the derivative of?
Cosine to the power of 5x.
Yeah, Brent. Yeah.
Is it negative cosine?
Okay, and so we've got a couple of different options. What can we do? Yeah, so this is what I was kind of tried to encourage you in your homework. Give it a shot. So Brent, what do you say? Negative cosine of x. I think. Do you mean this?
Yeah.
Okay, so sure, this is a good attempt. So let's go for it. So now, what do we do to check it?
Graph it against the.
We could, but there's a quicker way now.
Oh, just to write it.
Yeah, just take the derivative. Okay, so the derivative would be negative 5 cosine to the 4th x. Are we done? Times negative sine x. So if we got what we started with, then we have this right. How'd we do? So Brent, you want to change it?
Yeah, just get rid of the negative.
Yeah. So, and that's the other thing the check does. If you're wrong, the check allows you to make the right correction because you see what happens. So how about this? Does it work now? Yeah, so we have an antiderivative. The antiderivative would be cosine x, or cosine to the fifth x. And so can we, let's check our open form against the closed form. Or, sorry, other way around. Check our closed form against the open form. So remember, in graphing calculator, prime does not have anything to do with derivative. It's all about just opening up a new window screen and graphing on a new window screen. So just see those as a y and an x. So open form for this. Who can do it? Ross. Can you give me open form for this? Or sorry, closed form. Can you give me the closed form accumulation function for this open form with a restart or a reset at 0.5?
F of, oh no, sorry. Cosine of the fifth of x minus cosine of the fifth of 0.5.
So cosine. He said cosine of x to the fifth minus. Did you say 0.5 to the fifth? So this is review. Remember doing this? So that should land right on top. We'll do it. We'll do it. Right, so turn it off. There we go. So here's the open form accumulation with a restart or a reset at 0.5. And so if I turn on the closed form, it should land right on top, and it does. What's that? That just makes a new window over here. That has nothing to do with prime or derivative. Just see those y's and x's. It just makes a second screen over here. Question, Marco?
Oh, I was just asking if it was just going off of f of x minus f of c.
F of x, right? So we found that it was the antiderivative evaluated there minus the antiderivative. That's what we. That's. Yep. Okay. Does it make sense? Any questions? Okay, so the moment we've been working for all semester long, and it's really, there's hardly anything new to think about here. With this one. Fundamental theorem of calculus, this is it. If capital F is any antiderivative of little f, then, and little f then represents what kind of function in this context? Rate of change, right? So f in this context here represents a rate function. So then what does this represent in this context? Okay, be more specific. Open form accumulation. Okay, and so now this A has it's not the absolute starting point of accumulation, but it's kind of like we think this is like a restart. Or we think of that, it could be starting way before that, but then we force a restart or a zero accumulation at x equals A, okay? And so then all the fundamental theorem says is that the open form can be written in closed form with that antiderivative. And we've already done this, right? We've already done this. And so if we were to pick an actual value of x and accumulate from A to say B, then we would get an actual value now. So the first version of the fundamental theorem is accumulation function. That the open form of the accumulation function can be written as in closed form with any antiderivative of the rate function. And then the second part is, okay, so what about a specific We say net, we can call this like net change. Net change from x equals a to x equals b. Or net amount of accumulation. So the first one's a function, the second one is an actual amount, a value. And it's just, it's like falling out of bed. It's just plugging a value into your function, right? It's just plugging a value into your function and saying, okay, now how much accumulation do you get when you reach this given b value? Okay, so this property has enabled generations of people to do calculus exercises without understanding calculus. Okay, but we've worked 3 months to understand all of its meaning, right? All of its meaning. And so we've tried to do better than that. That's what I'm saying. We've tried to do a lot better than just, okay, here's another formula in another math class to plug numbers into. Okay. So let's take a look at this here. Let's check it out. And let's look at some rate functions, and we'll check the open form in graphing calculator, and then we'll figure out the closed form antiderivative. This is 100 too big. And then we'll check. Okay, so if you have a laptop and get up graphing calculator, and we'll kind of work together on this. Okay, so we'll start out with r of x equals cosine to the first one, and we can just change that, and then we'll have the open form, accumulation from 2 to 5, which is the integral, control shift I, the integral from 2 to 5. Of r t dt, and already I have a value. Already, as soon as you set up that integral, you get a value, in this case 0.1064. So we can write that down. Okay, so now how are we gonna? So we're checking the fundamental theorem, and we're checking this property. We're solving for the left side using graphing calculator, open form, and then we're gonna solve using the right side. So how do we check, and how do we solve the right side of this property? What do we need? So, Brian, we're going to check this right here. How are we going to check it?
We just plug in.
Plug into what?
2 and 5.
Okay. Into what?
So it would be f of 2 minus f of 5.
What is f?
The accumulation.
And what is that? Antiderivative. Okay, we made it. What's the antiderivative?
I think that's as far as I
Okay, did you do your homework?
Yes.
All right. Oh, well then you have lots of practice at this. Steve,
I don't know.
with cosine 2x, we're thinking, what question are we asking? What is this the derivative of?
That's
Kevin?
would it be just negatives? That would be negative sine
Negative sine
over 2
over 2.
Oh, negative sign, yeah. I believe that'll be negative sign 2x still. Yeah.
Okay, all right, so how can we check? Take the derivative. All right, so take the derivative of this. What is the derivative of negative sign? Derivative of negative sign is cosine. It'd be negative cosine, right? So do you want to adjust this? Yeah, so you're thinking, what is this the derivative of? Isn't cosine just the derivative of sine? Cosine is just the derivative of sine, but wisely you also saw that you need over 2. Okay, so we can say capital F of x is sine of 2x and then times 1/2. And now I'm checking out, how do I check my, if I'm integrating from 2 to 5, then I want the total accumulation of capital F up to 5 and then minus two. Did we get the same thing? So we're checking, we're solving, we are actually computing both sides and checking the property. Okay, is this the only antiderivative of cosine of 2x? Molly, give me another one. Is there another antiderivative of cosine of 2x?
Well, if cosine of x had a constant added to it,
Okay,
so it could be an infinite number of constants added
give me your favorite.
to 1.
Oh, so boring. All right, what about this? Is this an antiderivative of cosine 2x? So if I come up here and I change our f function to that same one plus 1, what about the f5 minus f2? Still the same. Why? Because it can be any antiderivative, right? Capital F can be any antiderivative. All right. What about plus 100 billion or whatever I did? Same. Keeps it the same, right? Okay, so I want you to work on these two for the next minute or two. So work on e to the minus x plus x, 3 over x plus 1. Find the value of the accumulation from 2 to 5 using the open form, and then using a closed form antiderivative. And pick any one that you want. Pick any closed form antiderivative that you want. Okay, work together and check.
Okay. So it's just it's the 2, this is because so we how would you just
Just this. Thank you.
Did you get 10.629 for open form? Okay, so we trust that one, right? We trust the open form. All right, how about an antiderivative then? If we're going to check the fundamental theorem, we need an antiderivative. Or in other words, what function has this as its derivative? Shannon, did you get it? What function has this as its derivative? So when we take a derivative and we get e to the something, where did that come from? Yeah, so e to that thing, right? So what about e to the minus x? Does that give a derivative of e to the minus x? Exactly. So if you took the derivative of that, would it give you e to the minus x? Not quite. There's one adjustment we have to make. We'd also multiply by -1 when we took the derivative, right? So, but we don't have a negative here. We don't have -1 here. So how can we account for that, or how can we compensate? So we end up getting the opposite of what we want. When we take the derivative of this, we end up getting the opposite of what we want. We get negative e to the minus x. We want positive e to the minus x. So how can we adjust this? All right, now does it work? Is the derivative of that? Yeah. Yeah, and if you're not sure, just try something close and take the derivative and compare them, and then that will give you the information of how to make the adjustment. So you don't have to. So this is what I see lots of students doing. They just stare at their paper like, I can't get it, I can't get it, I can't. Just write down something close, and then practice your mastery derivatives. Take the derivative, and then compare what you started with your derivative of your guess, and then see what adjustment you have to make. Don't be afraid to just go for it, and then take the derivative, find the closed form rate with the rules that you've mastered, right? Mastered, and then compare. All right, what about x? Somebody new. X. Melody.
I did 1/2 x squared plus
1/2 x squared. So if the power rule, when we do derivatives with the power rule, what? We reduce the power by 1. So what happens with an antiderivative? We're going to increase by 1, but then we may have to kind of clean up a mess here, right? So if we just put 2x, then our derivative, or sorry, if we just put x squared, the derivative would be 2x. We don't have 2x, we have 1x. So we need 1/2 then to make it, the derivative of that now is exactly x. And we know that adding and subtracting, we just go term by term. When we take derivatives, we just go term by term. So we're just going to add those two, and we got it. Questions on that? So the homework was just hopefully trying to get you into a warm-up of this. So now what is our antiderivative that we're using? Negative e to the minus x plus 1/2 x squared. Get the same thing? All right, did anyone have a different closed form antiderivative? Is there more than one? Plus what?
1,000.
You guys pick some really boring numbers. Just kidding. Does it change it? Nope. It's still good. So yeah, plus any constant, right? So that accumulation function can have a restart or a reset anywhere, right? It can be moved up or down, and that doesn't change how much accumulation you get from one point to another, right? Because it's it's a difference. It's a net change. So the net change, if you started with a huge accumulation already, 1,000, the net change from 2 to 5 will still be the same as if you started at an accumulation of 0. All right, anybody have a question? Does this make sense? So we're kind of doing two things at once here. We're practicing antiderivatives, and we're also simultaneously checking the fundamental theorem of calculus by comparing the open form from A to B to the closed form from A to B using the antiderivative. Anybody have a question? Okay, this last one. So how about this last one? The rate is 3 over x plus 1. And when I do that, I get 5.7489. Is that what you got? Okay, closed form antiderivative. Somebody new. Kaylin, how are these coming?
I tried 3 over, what did we do? X squared divided by 2, so 1/2.
Okay.
3 divided by 1/2 x squared.
So let's try that. So that's really basically 6x to the minus 2, right? So what's the derivative of 6x to the minus 2?
Negative
12x to the,
negative third.
how do we do? The same as 3 over x?
No.
No, not even close, right? So that's not close, because that's 3x to the minus 1.
Right.
So we got to think, what function has a derivative of 1 over x? What function has a derivative of 1 over x? Ryan?
3 natural log of x.
3 natural log of x. Remember, the natural log is the one. So that's the one case. When you have x to the minus 1, that's the one case where you don't reverse the power rule. You're not going backwards on the power rule. You got to be kind of on the lookout for it. It's natural log. Remember that? Natural log has the derivative of 3 over x. Yeah?
Does it throw it out drastically if you recall just a log, like
Yeah, because it's different base. Log of x means base 10.
this is all
Natural leg is base e. Yeah, that's drastically different, yes. So that's ln of x. This is log, so yeah, make sure it's ln. Okay, what function has a derivative of plus 1? X. Okay, and let's add something, pi to the 1726. Is that okay? Pi to the 1726? How about that? All right, so we got 3 ln x plus pi raised to the 1726. It didn't like that. So we'll just go with 1726. And we're good. 5.7489. Anybody have a question? Sure. Yeah.
So if we had changed the end values from 2 and 5 to -2, -9.
We would have a problem, a domain issue with some functions, right? So she's saying if we were from -2 to -5, these functions, the rates and the accumulations were good for all real numbers. But this function is only defined for what? X greater than 0. Okay, so it's time to try to do something, but it's certainly kind of worked.
Oh, it's 3 natural laws.
So what's happening is we can't, ln x is not defined for -5 and -2.
Oh, it doesn't exist.
Yeah, it doesn't exist. It only exists for positive values. Okay?
So is that where?
Do you have a, I mean, do you,
I intentionally asked the question.
Right, I know.
Just because, so the way I've always dealt with this issue is wanting to have the antiderivative defined everywhere the rate of change function is defined. So to address that issue, I put absolute values around the x. So the antiderivative of 1/x is the natural log of absolute x.
That's cheating.
But what it does is it maintains.
Yeah, it leaves it that way open, but.
so she's suggesting this. So by putting absolute value around the x, then we're putting in positive 5 and 2 into natural log, and now it works. I'd have to think more about why that works, though. So do you know why it works?
It's exactly. I mean, it's a choice that mathematicians made a long time ago to like make sure that they define so like in most textbooks, the antiderivative of 1/x is natural log of absolute value.
Right.
To maintain precisely to maintain the domain being the same.
Okay.
For the rate of change function and the accumulation function.
Yeah, in terms of, I'd have to. It's true. It works, and I would just it works, and maybe that's satisfying for you guys. For me, I would need to think more about it. I would like to, grapple with it and know why.
Well,
Yeah.
I want to know what's your reason? Why is this so off to you?
Why is it so off to me? It's not off. It's just something that I don't immediately understand why it works. Yeah. Because it's a different accumulation, right? So instead of going from so we're going from -2 to -5, but then this is.
Or doesn't absolute value just restrict the domain?
Yeah, but you're putting different x values into natural log than what you're accumulating from. You're accumulating from -2 to -5, but you end up putting 2 and 5 into this antiderivative. So why does that work? Yeah.
Well, I mean, maybe this is a dumb question, but can you accumulate like backwards like that? Because you're going from -2 to -5. I don't know, just because I just always kind of took it for granted, like it was like garbage.
Yeah. So we're accumulating from -2 to -5, and for the ln portion, we're actually plugging in 2 to 5 in the ln portion of that antiderivative. And I know it is correct. It gives the right result. But personally, I'd have to think more about it.
Isn't this function symmetrical with respect to the y-axis?
Would it be if the original function was not symmetrical?
You're saying that the rate is symmetrical?
Yeah, like if you were to draw a line,
Okay.
and split it, it'd be the same, so -5 to -2 and 2 to 5 would end up being actually the same shape.
So this 3x plus 1 looks like this. So yeah, it's something to do with that. You're on the good track there.
So you're saying the accumulation from -5 to 2 is the same as the accumulation from 5 backwards to 2. It makes sense.
I'm glad it does. Okay, so quiz tomorrow. So if there's homework for Wednesday, it will be a short, like a half homework, because you got your quiz this week and your exam on Thursday, which you want to focus on. So any homework for Wednesday will be this new stuff. It'll be less intense.
Does recitation
What's that? And Thursday. Yeah. That's fine. Yeah, sorry. Yeah.